Algebra 2, Chapter 1.1, Domain, Range, and Behavior, Homework Practice Exercises 11 to 15. So we're going to go over here. We've done the video already on exercise 1 through 10. And on this set, 11 through 15, on this video lesson, I'm going to do just problems 11 and 14. This set here, real world situations, is historically one of the more challenging things we do in algebra, the application of it. So we may be able to spend some time in class. Anyway, exercise 11 and 12, write a function that models a given situation, determine the domain for the situation, graph the function using that domain, and identify the range. Well, a bicyclist travels at a constant speed of 12 miles per hour for a total of 45 minutes. All right. So basically, for domain, well, our domain is going to be time. So I don't have a graph page here, so I'm just going to draw my own coordinate plane here. So drawing an XY coordinate plane. Okay, here we have time. And here we have miles. And it looks like a total of 45 minutes. So if we put minutes here, and here's one thing we can do. We can either go minutes or we can use hours. Well, one thing I'm going to do right off the bat is go to hours, and the reason is that we're given here 12 miles per hour. So it's going to be helpful for us to use time. Well, 45 minutes is going to be 0.75 hours. And how did I get that? Well, I know that 45 minutes is 3/4 of an hour. So here we go, hours, abbreviating hours. In miles, I don't know how far we went, but I know that our domain is going to be related to our x value, or independent variable. So I'm going to say domain is going to be equal to, use set notation for domain and range of the function. So we will say, we can just call this t for time, and miles we can call distance. So we will have t such that t is greater than or equal to 0, because we started at 0, and we went up to what? 0.75. And you could write it sometime to see it written at 0.75. Okay, and that's going to be in hours. So that's going to be our domain. And if you had written 0 to 45 and had this in minutes, well, that would be permissible too, right? And you know you're going 12 miles per hour. So based on that, we would have a function distance is equal to 12 times t. And this is only going to work in this form if we have our time, or independent variable, in hours. So 12t. So what you do is you multiply times t. So if I take this 0.75 and I multiply it by 12, we're going to get the distance covered in that time. Well, 0.75 is going to be 3/4 of 12, so it should be 9. Let's go ahead and work this out. 10, 2 times 7 is 14, plus 1 is 15. And then we have 1 times 0.75. Well, we have 75 goes here. So we have, that's going to be 0, 10, and that's going to be 1 plus 1 plus 1, that's going to be 9. And then we have 2 decimal places built in, so we have 9 miles. So if we go to 9 over here, we have covered, I'll just sort of horizontally place this here. Okay. So we go right to here. That's going to be the end point. If we want at constant speed, we go like this. Get a straighter relation, not super straight, but enough. So that's going to be the relation. And what's going to be our range? Well, our range, and I'll just write down here range in red. It's going to be distance such that our distance is going to be greater than or equal to 0, but less than or equal to 9, as in 9 miles. So there we have a domain and we have a range. Okay, I think that'll handle that one. Let's go on here to 14. Now, look at 12. We have a movement of an elevator in a tall building. So we can do this one similar to what we did in problem 11. Here we have a 13, explain the error. 14, which we're going to work on. And what are the domain, range, and behavior function? We have f of x equals x cubed. So let me get a skinnier line. Here we go. What are the domain, range, and end behavior of the function? Here we have x cubed. Well, this function here, f of x equals x cubed, that is a polynomial function. And what does it say? Using set notation and inequality as an inequality, using set notation and interval notation. So that's all three. Okay, basically, the pure function itself, the polynomial function, is all real numbers. So for our domain, which I'm going to write up here, is we have x is going to be greater than negative infinity, but less than positive infinity. And for our set notation, we have x such that x, and we can write this as an element of all real numbers, but I'm just going to go ahead and bring down the inequality notation with me. So where x is greater than negative infinity, but less than positive infinity. And we'll seal that off. And finally, in interval notation, we have open parentheses negative infinity, comma, positive infinity. And there we have it. Okay, let's see here. That's going to be our domain. Our range we have is going to be, well, it's going to be the same thing, except we would use that in y, or in this case we have f of x. Well, it says y on the graph here, so we'll just use y. We'll say range y is less than positive infinity, but greater than negative infinity. Our in set notation, we have y such that y is greater than negative infinity and less than positive infinity. And in interval notation, we have negative infinity, positive infinity. A little plus sign there. Okay, good. Next it says B, how is the range of the function affected if the domain is restricted to -4 to, well, it's -4 to 4. Well, first of all, we're going to find f of -4. If we put f of -4 in here, we're going to get -4 cubed, and -4 cubed is going to be -64. And then f of 4 is going to be, we're going to put 4 cubed. 4 cubed is 64. So basically, that's going to be our range. So it says inequality notation. So we'll say our range is going to be y is greater than or equal to -64, but less than or equal to 64. In set notation, it's going to be y such that y is greater than or equal to 64. There we go. But less than or equal to 64. And then finally, in interval notation, we would just go like this, brackets, -64, comma 64. And the last thing we have is part C, graph the function with restricted domain. Well, we know that we're going to be going from -4 to 4. And what I'm going to do is just superimpose in red over the graph of the original in blue. And we know we're going to come right down here. We know it's going to be the point -4, comma -64. That's that coordinate pair. And we're going to come up here, right above 4, to the coordinate pair 4, comma 64. And superimposing as best I can over the blue one, it'll be just like this. So there it is, graph. And there, all right. So that's it. You can go ahead and look at number 15, which is another real-world situation problem. Looks like there's a grid placed on here. I hope this has been helpful to you. Again, these problems seem to be more challenging, applying algebra to real-world situations, but that's what thinkers do. They apply mathematics in situations where possible. Good luck, and thanks for viewing.